Hey, welcome back. This is on now 9.3, and we're going to have two types of tests that will tell us whether or not a series converges. So, unlike before, we're not going to actually be able to find a formula for that S sub n thing, that sequence, that expression for the sequence of partial sums. So we won't be able to kind of like with the telescoping series, just take the limit and then you'll have your kind of your answer. This is more of does it converge or does it diverge type thing. So you'll be able to know if it what behavior it has, not necessarily the actual sum. The book will give you maybe some hints for if you really want the sum, you can do this or you can do that. We won't worry too much about it right now. So here at the bottom of the page, you can see some comments about doing approximations of these series. We won't worry too much about that just yet. Okay, it'll turn out so long as the series is convergent. All you have to do is take the first so many terms, depending on the amount of error you're willing to tolerate. You'll be able to get an approximation. Okay, so let's dive right in and look at this, the integral test and the P series. So we begin with the integral test. And it's fairly simple. Because we've done improper integrals, there'll be kind of a correlation between the summation, the infinite sum, or the series, and the integral. Okay, so you see that in Theorem 9.10 right there. I'll sort of write it out. We need f to be having certain characteristics. So we note that if this function f of x is positive, continuous, and decreasing. So if all those criteria hold, and it's true for some n value greater than or equal to, I guess, 1. So, I mean, the relationship we're talking about will be the relationship between this infinite series, a sub n, from n equals 1 to infinity, and this infinite integral from 1 to infinity of f of x. So maybe it's not even clear what f of x is, right? F of x is basically just a sub n, but over the real numbers. Okay, so f of x and a sub n will basically be the same thing. So for example, and I'll get back to writing the theorem out, but for example, you'll be comparing the series of 1 all over n and n equals 1 to infinity, and the integral from 1 to infinity of 1 over x dx. So that function f of x is basically just the formula for the terms of the series, but with an x instead of n. Okay, so that's the function we're talking about. So if f is positive, continuous, and decreasing for some value of x and beyond, so we'll say the book says for x greater than or equal to 1, and this a sub n will equal this f of x basically thing. So we'll write it like that: a sub n equals f of n. If those factors hold, then we will have this correspondence between the series and the integral, and either both will converge or both will diverge. So they'll end up having the same type of behavior. Either both converge or diverge. So ultimately, all you have to do if you're trying to figure out if a particular series, if you're trying to figure out the behavior of a particular series, and you know it's the terms of the series can be basically integrated over an infinite integral, over an infinite interval, then you'll be able to make a conclusion about that particular series. So why does this work? And the reason why is because you can kind of wedge the integral in between these inscribed rectangles and circumscribed rectangles, like you're seeing over here in figure 9.8. Okay, so the idea is you have this function f of x, continuous, decreasing, positive, and like that. Okay, And you're going to be able to kind of put the terms of the series as, or kind of illustrate the terms of the series as rectangles below the function or above the function. So when they're below, they call that inscribe. When it's above, they'll say it's circumscribed. Okay. And the key is to give them equal bases. So the lengths of the bases are always 1. Okay. 1, 2, 3, 4, dot, 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 all the way up to n minus 1 and then n. Okay, so the area of these rectangles will just be height times base. And because the base is always 1, I mean, the area is basically just the height, right? Because the area will be, okay, so for example, this rectangle, a sub I, or a sub 1 in this case, the area of that first rectangle is just f of 2 times the base, which is 1. So it's basically just f of 2. And because of the way we've kind of set things up, f of 2 is equal to a sub 2. Okay, so the area of these rectangles is basically just the beginning of the infinite series that we're concerned with. Okay, it's well, in this case, a sub 2 plus a sub 3 plus a sub 4 and on. So we can write it as the finite sum from I equals 2 to n of f of I if you want, or you can write it as a sub I. And then you could say, well, that's got to be less than or equal to the integral from 1 to n, because the integral from 1 to n is just all the area underneath the curve from 1 to n. And clearly that's going to be greater than the area of those rectangles, because it's going to include these kind of blue triangles at the top that you're going to be missing when you do the finite sum. So it's obviously greater. So you're going to have an integral of f of x dx. And then you could say that that integral is then less than the sum of the circumscribed rectangles. So you kind of have the same picture, but now you're going to plop the rectangles above using the right-hand endpoints. Okay, so again, you begin at 1, but now you use the right endpoints for the tops of the triangle. So 1, 2, etc. And you'll see that the area of those rectangles is greater than the area below the curve of f of x. 4 and on and on and on again. And then the last rectangle will be the n minus first rectangle this time. Okay, so this integral from 1 to n will be less than or equal to the sum of f of I from I equaling 1 to n minus 1. Okay, it's this relationship that you take advantage of, right? And you're kind of in order to prove that if the integral converges, the series converges, basically you just take the limit of these two parts of the inequality, right? So you'll be able to determine the convergence of the integral. So in the first case, if the integral converges, you end up with the following. So if the integral converges, you have basically the limit as n goes to infinity of this s sub n thing. I mean, technically it's s sub n minus the first term, right? So it starts at I equals 2, so you kind of have to subtract away f of 1. But it's not going to affect our sort of analysis here. And then this will be less than or equal to that integral from 1 to infinity of f of x dx, which we're saying is equal to some number, right? So basically what you have is a situation where your sequence of partial sums is bounded above. We also have the positivity of the terms of the sequence, which means that this sequence of partial sums is always going to be increasing, because you're always adding something to the next partial sum, right? So you have a sequence of partial sums that's increasing and bounded above. So by the monotonic convergence theorem, it's convergent. Okay, so let's write that out in human words. So in other words, the sequence of partial sums is increasing and bounded above, and we know from our chapter 9.1 that means it's convergent. Okay. Then moving on to the other sort of side of the inequality, you can take the limit of both sides of this thing, right? If your integral is diverging, the fact that your integral will go to infinity kind of forces the sequence of partial sums to also go to infinity, and therefore the series will diverge. Okay, so then on the other hand, so let's write that out. If the integral diverges, the inequality, so we can rewrite the inequality here. Basically, the integral from 1 to infinity of f of x dx sort of being below this limit of the partial sums, and it's technically not s sub n, it's s sub n minus 1, but it will have the same behavior as s sub n. So the fact that this thing diverges, the thing on the left, the integral, that implies the sequence of partial sums will diverge, and therefore the series will diverge. Okay, sequence of partial sums diverges, and basically that's it, right? So yeah, it's from this kind of weird geometric observation that we're able to kind of make these conclusions, right? Okay, so let's look at maybe some problems, then get away from the theory and look at some of the problems and what you're up against. So let's look at number, I guess, 2. And the first part of this, you still have to kind of make sure that the function you're working with is positive, continuous, and decreasing. Okay, this is a little different than when you're doing the monotonicity tests. You have to use calculus in these cases. Okay, so for proving the positivity, continuity, and decreasing, you're in the realm of calculus. Okay, this is not applied to the terms of the series, right? This is not done on a sub n, it's done on f of x. Okay, so here then we're looking at number 2, the series they give us. Let's write the series is 1 over 4 to the n, and first I need to, and it's going from n equals 1 to infinity. So I need to show it's continuous, positive, and decreasing. And in particular, we're working then with the function f of x equals 1 all over 4 to the x, where the domain is going from 1 to infinity, right? So I get the domain from the indexes or the limits on the integral. See how it goes from 1 to infinity there? That's how I get the domain. So you just need to make sure it works on this interval from 1 to infinity. You can always push that interval out. Like you could say, so long as it works from 8 to infinity, that will be good enough. Okay, so as long as it's eventually continuous, positive, and decreasing forever, that's good enough. Okay, so anyways, continuous. Is this function continuous? And certainly exponential functions are continuous. So yes, it's continuous on that interval. You know, it's technically it's kind of a rational function. You have 1 all over 4 to the x. You can note that the numerator will never equal 0. The only issue would be the denominator. equaling 0. And of course, that never will equal 0. So you're safe with regards to continuity. The only issue you would have is if the denominator was equal to 0, which it's not. You don't have to worry about the numerator, actually. Right. So, yes. Secondly, then, is it positive on this interval? So it's positive everywhere, right? So the numerator is 1, so we note that 1 is greater than 0, and then 4 to the x is also greater than 0. So what you have is a positive over a positive, so that will definitely be positive. In other words, it's greater than 0. So all of this junk implies that 1 all over 4 to the x is greater than 0, which implies it's positive. Okay, so that stuff's kind of, on a test you could basically just say yes. I don't need to see some logical argument. Maybe if later on you take more proof classes, if you're going to become like a math major, you can worry about that stuff there. Okay, thirdly then, is it decreasing? And this is what you would have to show on my test. I would definitely want to see your proof for decreasing on that interval from 1 to infinity. How do I do that? Well, here, because you're dealing with a function, you're going to look at the derivative. Okay, the terms of the series are functions as well, but they're over the set of integers. Here we're dealing with a continuous function. We could take the derivative, so let's do that. So I have f of x equals 1 all over 4 to the x, f prime of x, and let's rewrite this thing, right? So this is really the same as 4 to the negative x. Okay, so f prime of x will be 4 to the negative x times the ln of 4 times negative 1. Okay, from the chain rule and the rules for taking derivatives of exponential functions. If you don't remember that, how did that work? 4 to the negative x is equal to e to the ln of 4 to the negative x, which is equal to e to the negative ln of 4. There should be an x. Power rule it. So bring the negative x out in front. So you'd have e to the negative x ln 4. Then the derivative of that thing, of course, you just get y prime equals e to the negative x ln 4 times the derivative of negative x ln 4. I'm trying to give myself a little more room here. Which is negative ln of 4. Okay, and of course e to the negative x ln 4 is just 4 to the negative x, so you can back sub ln 4, and that's exactly what I got. All right, so here it is, negative 4 to the negative x ln 4. 4 to the negative x is greater than 0, ln of 4 is greater than 0, and then there's that negative in front. So you have a positive times a negative. That is certainly negative, and it will be less than 0. Okay, so it's decreasing on this interval from 1 to infinity. And so therefore we have all three criteria holding, and we can apply then the integral test. Okay, so you need to do these kind of, you could wave your hand about these and you just write yes, but on the test I would definitely need to see this derivative part, okay, the third part. Right, so anyways, once you get through that, then you're back to doing an integral. So integral from 1 to infinity, so over the domain, basically, of 1 over 4 to the x. Let's rewrite that as 4 to the negative x dx. And then we could rewrite it as a limit as b goes to infinity from 1 to b of 4 to the negative x dx. You do a u sub, you'd have a negative floating around, and then the integral for the u is going to be 4 to the u over ln 4. Back subbing, then you'll have limit as b goes to infinity of 4 to the negative x all over ln 4 from 1 to b, and then substitute in the limits, b to infinity of 4 to the negative b all over ln 4 minus 4 to the negative 1 all over ln 4. And taking the limit, then, what did I lose? I lost my negative somewhere. There should be a negative kind of floating about. Then taking the limit, the first part, because it has a negative exponent here on the b, all the terms will drop to the denominator. It'd be like 4 to the 10th, 4 to the 100th, 4 to the thousandths in the denominator. So the denominator is going to get huge, and it's just going to end up going to 0. At least this first part will just go to 0. The second part is just a constant, so you'll end up with 1 all over 4 ln 4 as your answer, and therefore it'll converge. So both will converge. Again, it's not converging to that number, right? The integral and the series can be different. So you won't be able to say that the series will equal that. It'll be close probably, but it won't be the same. So 1 all over 4 ln 4, and it's converging, and then do a drum roll. Did I get it? Yeah. Okay, let's look at number 5, see what's going on there. We have the series from n equals 1 to infinity of the ln of n all over n to the 7th. So we're considering the function f of x equals ln x all over x to the 7th. And the domain for this guy is going to be from 1 to infinity, supposedly. Okay, so we want to go through and show all the rigmarole is true. So first, is it continuous? Ln of x is continuous from 1 to infinity. X to the 7th is also continuous from 1 to infinity, and it's never 0. So you're good with respect to continuity. I mean, the only issue would be if the denominator is equal to 0, which it's not on this interval. So it's continuous. Secondly, then, is it positive? So certainly ln of x is greater than, so it's greater than or equal to 0 on that. So it's technically not positive at 1, but if you want to, you can always say it's positive from 2 to infinity if you want to play that game. Okay, so we'll say yes, and then just kind of push out the domain a little bit so it works. So on 2 to infinity, when we go to our integral, we're going to have to go back to 1 to infinity because that's what they want in webassign here. Thirdly, is it decreasing? So again, what you do here is go to the derivative f prime of x. Okay, so that will be low d high, low times the derivative of the high minus high times the derivative of the low, all over the low squared. Let's clean it up a little bit. So get x to the 6 minus 7 x to the 6 times ln of x all over x to the 14. Then, so this is a question. I'm going to factor out the x to the 6 from the numerator. I get 1 minus 7 ln x all over x to the 14. You could simplify that a little bit. So I get 1 minus 7 ln x all over x to the 8th, I believe. And then on the interval from 1 to infinity, let's look at it on there. See if it's actually decreasing. Basically, you have to find the critical points in that interval. There's a critical point at 0, but it's not in the interval, so you could kind of toss that out. Actually, the function isn't even defined at 0, so it wouldn't even be an issue. So anyways, all you have to basically do is take the numerator and set it equal to 0 for the critical numbers. You can learn how to do that in Calc 1. Solve this equation, so you get 7 ln x equals 1, ln x equals 1/7, and then x equals ln of, x equals, you have to exponentiate. So exponentiating both sides, e to the ln of x equals e to the 1 over 7. E to the ln of x is x equals e to the 1 over 7. You can figure out what the heck that is in the calculator. Do I have an exponent? Yeah. E to the parentheses 1 divided by 7 and parentheses 0.14. So x 0.14 about. So on our in our domain, that's not even in there, right? So we're just looking from 1 to infinity. So the sign will always be the same, and so plugging in something like e to the let's say 2 over 7, right? So look at a test point e to the 2 over 7. If you plug that into the derivative here back above, you'll have 1 minus 7 ln of e to the 2 over 7 all over e to the 2 over 7 to the 8th. And the denominator will be positive. You just have to worry about the numerator. So what is the numerator? That'll be 1 minus 7 times 2 over 7, which will be 1 minus 2, which is clearly negative. In other words, the function is decreasing on that interval. So hence, f of x is decreasing on the interval from 1 to infinity. Okay, so you definitely have to do that kind of analysis on the derivative to show it's decreasing on my test. And so it becomes kind of like a Calc 1 problem where you're finding the derivative, get the critical points, do your number line, find the sign of the derivative. It should be negative if it's decreasing, and then you can make your conclusion. Okay, so yeah, we're done with that part. Now we can go to our actual integral test. We're going to go from 1 to infinity. You should probably do 2 to infinity because we found that it's not technically positive if it equals 0 at one of the endpoints. But we'll just go with what the book wants. So we have 1 all over, in my opinion, there's a series 1 to infinity, 1 over x cubed dx. Whoops, that's the wrong one. That's what happens when I can't see the board. Here, let me push this over. What do we have? ln of x over x to the 7th. Looks like we're going to have to do by parts on that thing. You can make u equal ln x, and then dv is going to be 1 over x to the 7th. In other words, x to the negative 7, right? And then v, add 1 to the old exponent, so it would be x to the negative 6, divide now by the new exponent, so it's going to be negative x over x to the negative 6 over 6. Du of this guy is 1 over x. Okay, so let's rewrite it. Change it to a limit as b goes to infinity of 1 to b of this jazz. So actually we need to erase this and do the by parts. Okay, so I got what? This times this, so negative ln x all over 6x to the 6, then minus the integral of that times that, so it'll become a plus. There's a 1/6 to pull out, and then you have x to the negative 7 dx. That should be easy enough to do. Limit as b goes to infinity of negative ln x all over 6x to the 6. This will become a minus 1 all over, so adding 1 to the old exponent, negative 7 plus 1 is negative 6. So dividing by the new exponent, you get a 36x to the 6, I believe. And then the limit as b goes to infinity. This thing, technically, I got to do a L'Hopital's on it, right? So it would end up being negative 1 over x all over 36x to the 5th. Then that would be negative 1 all over 36x to the 6th. And as sorry, it should be a b because we need to evaluate this from 1 to b. So I'm not even done yet, right? I still got to do that part of it. Getting a little bit ahead of myself. I apologize. So we have the limit of negative ln of b all over 6b to the 6. that will go to 0. Minus 1 all over 36b to the 6, that will go to 0. Minus, plug 1 in there. ln of 1 is 0, so the first term is 0. And then minus, plugging in 1 into that guy, that would be minus 1 over 36. Okay. And like I said, this guy is going to go to 0 because of it's going to be a L'Hopital's, right? So it would be kind of like, instead of x, I need a b here, but just letting b go to infinity. So the limit of this thing as b goes to infinity, it's going to be an L over infinity form, so it's just going to be 0. And then this thing will also go to 0. So the denominator is just going to get huge, and you're just going to be left with 1 over 36. Okay. So let's put that in there. 1 over 36, so it is convergent as well. Okay. Whoops, screw that up. Let me pause video, find what I did wrong. Oh, I think I just put the answer into the... Sorry. I put it in the wrong place there. Converges. Hopefully that's it. Yeah, so it's refusing to let me put it. Okay, so yeah, that's the answer. So they're a little bit tedious in regards to the, the continuous positive decreasing part. You have to do all that before you can even do the test. But yeah. This isn't a test that you probably do very often. It's basically when you get handed a random series, if you think you can do the integral of the terms of that series, like you're looking at like number 4 there, I could easily do the integral of 1 over 2x plus 6. And you think, well, let's do an integral test, right? And that's kind of where you would employ this test. The test after this is a P series test, and basically you can prove the P series by using the integral test. Okay, so that's why we do it. So let's go to that section. Section 2. We have P series, and of course the harmonic series is a P series. And so first, the harmonic series is just 1 over n from n equals 1 to infinity. It's 1 plus 1/2 plus 1/3 plus dot dot dot. And this thing is divergent. Okay, it's extremely slow. Okay, but it is divergent. And you could kind of look at the term of the expression for the terms of the series, the 1 over n, and look at the integral of 1 over x, right? And if you go through the rigmarole, this thing's going to be continuous positive and decreasing, the 1 over x's. But at the end of the day, it's just a natural log. And as the natural log goes to infinity, of course, that thing is going to go to infinity. So, just very quickly, I'm going to rewrite this as the integral from 1 to b of 1 over x dx. That'll equal the limit as b goes to infinity of ln of x from 1 to b, and then we go limit as b goes to infinity of the ln of b minus the ln of 1 is just 0. Okay, and as b goes to infinity, the ln of b will also go to infinity. So therefore, we kind of just proven that the harmonic series is divergent using the integral test. Okay. In general, then, P series look like what's right here. So this first guy is the harmonic series, which you should all know. The second guy is a P series. Okay. So the P series will be like 1 over n to the p, where p is some constant that does not change. So you'll have like 1 plus 1 all over 2 to the p plus 1 over 3 to the p plus dot dot dot. And this thing then will converge when p is greater than 1, and diverge if, or rather when, p is greater than 0 and less than or equal to 1. Okay, so you should be able to kind of just look at these integrals and know when they diverge or converge. For example, number 7, there, and the homework is going to, I think it'll converge. Okay, so let's rewrite it so it's clear what it is. So I have, what is it? 1 plus 1 all over 8 is really 2 cubed, right? 2 cubed, square root of 2, plus 27 is really 3 cubed, square root 3, plus dot dot dot. So rewriting it as a series, it's a series from, I guess, let's say n equals 1 to infinity of 1 all over n cubed square root of n, which we can rewrite as a P series, right? N equals 1 to infinity of 1 all over n cubed times n to the 1/2. And then you can rewrite that as a series from n equals 1 to infinity of 1 all over n to the 6/2 times n to the 1/2 is n to the 7/2. We note the p-value then. So when you're stating this on a test, how would I say that? I would say something like it's a convergent P series. So you have to say whether it converges or not. Then you have to tell me what kind of series it is, P series. And then you have to tell me the criteria that makes it convergent. So here P is equal to 7/2, which is greater than 1. Okay. So you need to show me those three things on a test. You can't just flip a coin and say, oh, this one's convergent because that's what the gods on Mount Olympus are telling me. No, you have to tell me is it convergent or in some sort of order, the type of series and then its criteria. Okay, so that's kind of the big and the small of it. Let's see if there's any other. Okay, so the Riemann zeta guy down here at the bottom is a function you come across in like more math circles really than anything else. There's some outstanding hypotheses on the Riemann zeta function. There's books written on it. Anyways, it's a part of, I guess, number theory. And in this question, we just want to know where the heck this series converges. And if you look at the series, what is it? Well, it's a P series, right? But here the p-value is x. So you could rewrite it, make it look a little bit more familiar. It's 1 all over n to the p, or n to the x rather, right? But anyways, we know this thing will converge when x or p is greater than 1. Okay, so this will converges when x is greater than 1. They want you to write your answer as an interval, and you can kind of see my answer over there from 1 to infinity. Okay, so I think that'll do it for this video. As usual, thank you for watching, and we'll see you next time.